Hello and welcome back to the second part of this video lecture on study material 3 on polynuclear aromatic hydrocarbon. Just now আমরা বেশ কতগুলো রিঅ্যাকশন দেখেছি অ্যানথ্রাসিন সিনথেসিস করার এবং ফেনান্থ্রিন তৈরি করার একটা বেসিক রিঅ্যাকশন দেখেছি। কিন্তু ফেনান্থ্রিন তৈরি করার দি মোস্ট পপুলার টেকনিক till date remains the Bardhan-Sengupta synthesis, which was devised by Jogendra Chandra Bardhan and Suresh Chandra Sengupta, who did most of their work in Presidency College and the Rajabajar Science College as we know it, the University College of Science, Technology and Agriculture in Rajabajar campus. So this reaction still remains one of the main toolkit to synthesize phenanthrene nucleus. এটা রেট্রোসিনথেটিক অ্যানালিসিস করলে আমরা বুঝতে পারবো যে 1932 সালের যে পাবলিকেশন হয়েছিল বর্ধন-সেনগুপ্ত সিনথেসিস সেটা কি ধরনের একটা এলিগেন্ট সিনথেসিস ছিল। শর্ট সিনথেসিসে যেরকম এই বন্ডটাকে টার্গেট করা হয়েছিল বাইফিনাইল লিঙ্কেজটাকে, বর্ধন-সেনগুপ্ত এই বন্ডটাকে টার্গেট করেছিল। এবং এই দুজন বাঙালি কেমিস্টের লজিকটা ছিল এরকম যে এই জায়গাটায় যদি আমরা if I think of this as a target that can be accessed from a corresponding hydrated compound, যেটা dehydrogenation reaction করলে এই কম্পাউন্ডটা তৈরি হবে, then let us target this thing, because in that case this is basically nothing but formation of this bond is basically nothing but a Friedel-Crafts alkylation reaction on this aromatic ring, internal Friedel-Crafts alkylation, not acylation, Friedel-Crafts alkylation. So obviously এইটা আমাদের এখানে এটা আমরা অর্গানোক্লোরাইড বা অ্যালকোহল বা অ্যালকিন এই জায়গা থেকে আসতে পারে। তো ওনারা অ্যালকোহল সিলেক্ট করেছিলেন, যে জায়গাটা ওয়েজ থাকবে এখানে ক্যাটায়ন তৈরি হবে, ও গিয়ে ধরে নেবে। সো থিঙ্ক অফ ইন দিস টার্মস যে এই কার্বনিলটা আমরা কোথায় পাবো, আর ডেফিনেটলি এই ওয়েজটা আমরা পাবো কোথেকে? দিস সেকেন্ডারি অ্যালকোহল ক্যান বি অ্যাক্সেস ফ্রম আ কিটোন, and this ketone gives rise to a cyclohexanol moiety where the alpha position has been functionalized by CH2 pH. So this is a alpha alkyl ketone. Alpha alkyl ketone তৈরি করার টেকনিক হচ্ছে alkylation technique. For successful alkylation, they proceeded with a CO280 group installed here so that the anion can be stabilized, and we had a pH CH2Br. So this red phenyl ring will eventually end up here, and this blue cyclohexanone 6 carbon unit will end up here, and the side chain 2 carbon that will end up here. This is how the reaction was supposed to work, and they made it work. These two eminent Bengali chemists. এই একমাত্র এই রিয়াকশনটাই আছে যেটা বাঙালিদের করা, যেটা এখনো অবধি সমস্ত নেম রিয়াকশনের বইতে খুঁজে পাওয়া যায়। ভবিষ্যতে হয়তো আরো হতে পারে, কিন্তু এখনো অবধি এইটাই আছে যেটা সব থেকে জনপ্রিয়। এর বাইরেও বাঙালিদের করা নেম রিয়াকশন হয়তো রয়েছে, কিন্তু সেগুলো এত জনপ্রিয় নয়। তো প্রথমে অ্যাক্টিভেটেড সাইক্লোহেক্সানোন কম্পাউন্ডটা নিয়ে তার থেকে অ্যানায়ন তৈরি করে বেঞ্জিন মিডিয়ামে পটাশিয়াম দিয়ে তার সাথে আমাদের অ্যালকাইলেটিং এজেন্টটা দিয়ে রিফ্লাক্স করা হলো, করলে আমাদের অ্যালকাইলেশন রিয়াকশনটা হবে। এখানে সোডিয়াম বা ইত্যাদি ইউজ করা হয় না, বিকজ সোডিয়াম সল্টটা ওয়াজ ফাউন্ড টু বি ইনসoluble in the reaction medium, therefore potassium was the better choice. Now this thing was supposed to undergo hydrolysis followed by decarboxylation, which they attempted. The reaction worked, but the problem was the yield was very low and the rate was very slow. Possible interference from reverse Claisen reaction, because we know that this type of compounds, যেখানে এটাকে যদি তুমি আর বলে ধরে নাও, তো এখানে অ্যালকালি টাইপ কম্পাউন্ড বা ইথক্সাইড টাইপ কম্পাউন্ড যদি দাও তাহলে এখানে রিভার্স Claisen হতে পারে by attacking this carbonyl and opening up and then breaking this particular carbon-carbon bond. Reverse Claisen is one of the distinct possibility. The other possibility is that alpha carbon is so sterically congested that the reaction is kind of difficult on this carbonyl group, but they proceeded nonetheless with this. And তারপরে এটাকে যদি সোডিয়াম ইথার দিয়ে এই ডিকার্বক্সিলেশন হয়ে যাওয়ার পর এটাকে রিডিউস করা হয়, তাহলে আমাদের করেসপন্ডিং অ্যালকোহলটা পাবো 2-beta phenyl ethyl cyclohexanol, which will undergo under a drastic condition of Friedel-Crafts alkylation to give you this. And এবার যদি এটাকে পাউডার সেলেনিয়াম দিয়ে তুমি হিট করো, তো তাহলে ওটা ফুললি অ্যারোমাটাইজ করা যাবে। দিস ইজ 1 2 3 4 9 10 11 12 1 2 1 2 3 4 9 10 11 12. Obviously this is a octahydrophenanthrene nucleus. I have used 11 12 here, but it is actually for phenanthrene you cannot use the term 11 12, then you will say 10A 10B etc etc 9A 9B etc etc. But এটা যেহেতু phenanthrene ডেরিভেটিভ নয়, তাই আমরা এই দুটো রিং জাংচারকেও কিন্তু নাম্বার দিচ্ছি 11 12 এই নাম্বারটা দিচ্ছি। সো দিস ইজ octahydrophenanthrene, but under persuasion it will give up its additional hydrogens to gain aromaticity and become phenanthrene. But this step remained problematic, and when they published, they also published a solution for this. এবং এর সলিউশনটা ছিল এরকম যে এই জিনিসটাকে ডিকার্বক্সিলেট করো না, এখন এটাকে রেখে দাও, এটাকে আগে রিডাকশনটা করে নাও। এটাকে রিডাকশন করে নিলে এটা ওই ছিল। এবার এখানটায় যদি আমি P2O5 হিট দিই তাহলে এখানে আমাদের নতুন বন্ড তৈরি হতে কোনো অসুবিধে নেই, এবং এখানে নতুন বন্ড তৈরি হবে, এই বন্ডটা নতুন তৈরি হলো। অ্যান্ড দেন এটাকে যখন দেখা গেলো যে এটাকে পাউডার সেলেনিয়াম দিয়ে হিট করলে এখান থেকে যেরকম হাইড্রোজেন উড়ে যেতে পারে, বিকজ আই হ্যাড হাইড্রোজেন হিয়ার, এখান থেকে ডিকার্বক্সিলেশন হয়ে যাচ্ছে, CO2 চলে যাচ্ছে। তার মানে ester hydrolysis as well as followed by decarboxylation, everything is happening in this step, and they got phenanthrene. So this step was essentially avoided. So let us check the synthetic versatility of phenanthrene synthesis by Bardhan-Sengupta's method. কিভাবে আমরা এটা তৈরি করতে পারি? আমি এখানে কতগুলো রেট্রোসিনথেটিক অ্যানালিসিস দেখিয়েছি, বাট ফরওয়ার্ড সিনথেসিস গুলো বইতে রয়েছে, তুমি you can check them out and or you can try them by yourself. So this is the basic synthetic scheme that we have. Synthesis of phenanthrene from the corresponding hydrated derivative, hydrogenated derivative, and this hydrogenated thing will come from a Friedel-Crafts alkylation, which will come from an alcohol, which will come from a carbonyl, and this carbonyl is accessed by the alpha alkylation of cyclohexanone. So let us think of this. আমি এখানে কালার কোড করে দিয়েছি। সো এই পার্টটা obviously red part and two black carbons will come from here, and this thing, this blue ring, will come from a methyl substituted cyclohexanone where alpha position is activated by CO2. Okay, 2-methyl phenanthrene we can synthesize like that. What about 1,4,7 trimethyl phenanthrene? So obviously I'll need the red part এ দুটো মিথাইল সাবস্টিটিউশন থাকবে, ব্লু পার্টে একটা মিথাইল সাবস্টিটিউশন থাকবে। যদি আমার কাছে 1,4 ডাইমিথাইল phenanthrene থাকে, তো তাহলে আমি রেড পার্টে দুটো মিথাইল সাবস্টিটিউশন নেব এবং ব্লু পার্টটা unsubstituted. Unsubstituted means I have only the CO2 and the carbonyl and nothing else. What about 1,7 dimethyl phenanthrene, which is known as primethrene? তো of course আমার রেড পার্টে আমার মিথাইল সাবস্টিটিউশন থাকবে, একটা সাবস্টিটিউশন থাকবে, এবং সেটা থাকবে অর্থো টু দ্য CH2CH2Br, আর এই জায়গাটাতে আমাদের এখানে 4 পজিশনে আমরা একটা মিথাইল সাবস্টিটিউশন নেব ব্লু রিং এর মধ্যে। What about retine, 7 isopropyl 1 methyl phenanthrene, methyl ortho to CH2CH2Br on the red ring, and at C4 এ একটা isopropyl group at the C4 of the cyclohexanone. So you can think of many different possibilities, and Bardhan-Sengupta synthesis works for almost all of them. I want you to remember this disconnection specifically when we are going to discuss the next part and the last part of this video lecture. That is the Bogert-Cook synthesis. These things were done by American chemist Marston Bogert and British chemist J.W. Cook. They developed this reaction independently, but they arrived at the same type of conclusion and they published their result. But this year is important, 1933, and this year is important, 1932. So chronologically, Bardhan-Sengupta synthesis was published before Bogert-Cook synthesis. There is no way of knowing that whether this work of Bardhan-Sengupta inspired the Bogert-Cook synthesis or not. But what Bogert and Cook did in their paper was that they sort of tried to undermine the work of Bardhan and Sengupta by saying that it is essentially an extension of the Howard synthesis of phenanthrene. Nothing could be further from the truth, because it has got absolutely no similarity whatsoever with the Howard synthesis. This is not a 4-carbon unit which was introduced via a Friedel-Crafts alkylation. This is essentially a Friedel-Crafts acylation. This is essentially a Friedel-Crafts reaction, but this is alkylation. So this is fundamentally different. The whole construction is fundamentally different, but they nonetheless tried to undermine their work. Most probably because they wanted to highlight their work. And their work, if you look at them, this is essentially an inspiration, quote-unquote inspiration from the Bardhan-Sengupta synthesis. The same disconnections, same hydrogenated derivative থেকে phenanthrene বানানো হবে, same bondটাকে target করছে, same alkylation technique target করছে, but instead of using an alcohol, as you have seen in Friedel-Crafts reaction, you can take organochloride, organohalides, you can take alcohol, you can take an alkene. Instead of taking an OH, they are taking a carbon-carbon double bond. And this carbon-carbon double bond, they devised that this will be introduced via a dehydration reaction of the tertiary alcohol. And this tertiary alcohol will come from, surprise, surprise, this one and that one. So this one, this pH CH2CH2Br, and this one, this cyclohexanone. So this time this was the nucleophile and this was the electrophile. Here the reducer, the chemistry is changed. This is the nucleophile and this is the electrophile. You can only do so much with the given structure of your molecules. But there is no way to prove, and I don't contend to prove, that Bogert-Cook synthesis was totally inspired by that of Bardhan-Sengupta. But it is a written fact, published fact, that they went out of their way to undermine the Bardhan-Sengupta synthesis if you read the original papers. Dr. Chandan Saha and Dr. Suchandra Chakraborty has published openly available, freely available, open access article on resonance. I think you should consider that, reading that in your spare time. When you get some time, read that. The total saga is described there. So how did the Bogert-Cook synthesis proceed? So you have this 2-phenyl ethyl bromide converted to Grignard standard reaction. Add this to cyclohexanone, again standard, get the tertiary alcohol, and now think about dehydrating this. This dehydrating, this would be a problem, as I have put an asterisk here. Let us suppose that the dehydration proceeds. So এখানে আমাদের এখানে double bond তৈরি হবে. If I have a double bond, then of course under this reaction condition I can expect the intramolecular Friedel-Crafts alkylation to take place, and then selenium heating will give you the phenanthrene nucleus. So you can see that the starting materials are like the same, the approach is same, the sequence of reactions are basically the same. So Bogert-Cook synthesis can be logically said, even though there was no inspiration or no knowledge of the Bardhan-Sengupta synthesis available either to Bogert or to Cook, which was surprising because these results were published in very good journals, and therefore those journals were at least widely available. Not that this was published in some esoteric journal or in some Russian journal or in some German journal which neither Bogert nor Cook had access to. That was not like that. Those were published in very prominent journals, and therefore the whole synthesis, at least it looks to me, that it is the logical extension of the Bardhan-Sengupta synthesis. And perhaps Bogert and Cook, after doing their work, even though they were not inspired by Bardhan-Sengupta synthesis, they realized that this looks like a kind of an extension. So they went out of their way to undermine the Bardhan-Sengupta synthesis to highlight their work. They said that this is nothing but Howard synthesis. If this is an inspiration of Howard synthesis, then what is this? This is also an inspiration of Howard synthesis. If they try to undermine any way this synthesis, then their synthesis is also lacking in the same respect. At least equipped with the retrosynthetic analysis that we can perform at undergraduate level. At this level, we can at least understand that how similar these two syntheses are, and undermining one synthesis at the expense of other is impossible. Either you appreciate both or you don't appreciate any of them. Anyway, the problematic step, what was the problem here? The problem was when they tried to dehydrate this thing, probably the alkene was forming, but at this point you are needing a carbocation here. So you need a carbocation here, but that's a secondary carbocation. Why should it form? Because there is a chance that it can lead to a regioselectively more stable tertiary carbocation. If that happens, then you are gone, because then the bond will be forming here and not here. And in that case, you are getting a spiro compound, and that's actually what they isolated. So they realized that we have a problem. We have a problem here because the carbon-carbon double bond is generated, but the positive charge is not here as we require. The positive charge is here. Or it could be that this thing is actually directly giving access to the carbocation. Instead of any kind of elimination or something like that, we are getting the spiro compound. The problem remains. Tertiary carbocation will be forming in a greater amount compared to the secondary carbocation. Even though the secondary carbocation is forming, maybe it is isomerizing to tertiary carbocation, because carbocation isomerization is very fast. And then only the intramolecular reaction is, Fieldcraft reaction is taking place, because that's not a very easy reaction to happen. So how to solve that? If I can somehow make this position tertiary, then there will be a fair competition. And if I can somehow substitute this position with a group which will impart stability to the carbon-carbon double bond, this time it's we have a tertiary, we have a tri-substituted double bond. So maybe make it tetra-substituted double bond by introducing a methyl group here. So instead of cyclohexanone, use 2-methyl cyclohexanone. The blue methyl actually serves the function of stabilizing the double bond here, in providing incentive to form the double bond here, and providing incentive to form a carbocation here, because if we get a carbocation here, then this is also tertiary. And spiro compound is not very easy to form, but it was forming here as the tertiary carbocation was winning hands down over the secondary carbocation. But this time you have a secondary carbocation, possibility of a secondary carbocation formation here. তো সেকেন্ডারি কার্বোক্যাটায়ন যদি এখানে তৈরি হয়, তাহলে এই দিকটায় আর কার্বোক্যাটায়ন তৈরি হবে না, বা হলেও সেখানে রিং ক্লোজারটা will not be facile. Ring closure will be much more facile here, and therefore I get a methyl here. This methyl won't pose a problem, just like the in Bardhan-Sengupta synthesis, this CO2 didn't pose a problem. After they heated with powdered selenium, this thing was knocked off. So the same thing happened here. So they do the selenium heating and you get a phenanthrene derivative, and the methyl goes. So that's how the Bogert-Cook synthesis works. But essentially it is a logical extension, at least in my opinion, and in the opinion of many others. It is the logical extension of the Bardhan-Sengupta synthesis. দুটো জায়গা থেকেই কোশ্চেন দেয়, পার্টিকুলারলি Bardhan-Sengupta থেকে তো অনেকটা কোশ্চেন দিতে পারে তোমাকে, কি করে বানায়, রেট্রোসিনথেটিক অ্যানালিসিস লেখো ইত্যাদি। কাজেই এই জায়গাগুলো আমাদেরকে ভালো করে পড়তে হবে। এছাড়াও Bardhan-Sengupta synthesis, again I reiterate, we are Bengalis, so it is a matter of pride for us that these two chemists did what they did at that point of time, despite severe limitations. They devised a reaction which is still being taught. যখনই তুমি phenanthrene synthesis পড়বে, তখনই দেখবে ওয়ার্ল্ড ওয়াইড যেখানেই পড়ো, Bardhan-Sengupta synthesisকে বাদ দিয়ে phenanthrene synthesis পড়ার কোনো উপায় নেই। So thank you for your patience, and this lecture ends here.